Okay, you've done it. You've reached the last screencast of your AP Physics 1 year. Congratulations. Let's go ahead and learn about this. It's a special case of angular momentum, and it's the angular momentum of objects that are traveling in straight lines. That's right, you heard me correctly. An object traveling in a straight line can still have angular momentum. Let's see how that can work out. So imagine this. I've got a board sitting here, and I'm looking down on it from above. Okay, so let's say I have a hockey puck. It's traveling towards a board. They're both on this frictionless ice surface. This board is fixed to the floor in such a way that it can rotate around this pivot point here. Okay. Well, right now this board is not rotating, right? But when this ball hits it, that board is going to start to rotate, and that means it has angular momentum. Now, you can't create angular momentum, right? It's always conserved. So what that tells us is that the system must have had angular momentum before the collision. So this ball must have had angular momentum with respect to this board prior to the collision. Otherwise, we couldn't have angular momentum afterwards. So it's kind of strange. An object traveling in a straight line still has angular momentum with respect to some other point in space. Okay. So let's just see what that means. Okay. I think the best way to, for me at least, to really come to terms with this idea is to imagine, remember those like launches we had for launching the metal balls earlier in the year when we were doing two-dimensional kinematics and you shot it in the air and it landed in a cup. Okay, imagine I have one of those spring-loaded ball launchers. Let's just for sake of convenience, let's say it has mass m, and the ball it's launching also has mass m. And again, we're looking down on it from above. It's on a frictionless surface. There's a light rod of negligible mass connected to its pivot point, so it can spin this way. But right now, it's at rest. So the fact that the system is at rest tells me that the angular momentum of the system is zero. All right. And if no outside torque acts on the system, it's going to stay zero. And I'm not going to let any outside torque act on. I'm going to have a remote control. So there's no outside torque. When I hit this thing, it releases the spring. The spring is going to push the ball this way, giving the ball velocity to the left. And that same force is going to push this launcher to the right. And since it's fixed to a pivot, it's going to swing around in a circle, meaning it has negative angular momentum. So therefore, this ball must have positive angular momentum. Otherwise, the momentum of the system wouldn't be zero. So the idea is whatever the angular momentum of this spring loaded launcher is in the clockwise direction, this ball going in the counterclockwise direction, even though it's going in a straight line, it has the same amount of angular momentum, which I just said. So I'm not going to do that slide. Okay. So this is the equation you need to learn for this. This is the equation for the angular momentum L of an object traveling in a straight line. So this object here has this much angular momentum. Now let's just think about it. Again, we're looking down on above. This is a hockey puck. This is a board that can pivot around point P. Okay. Now think about this. It let's just say I have a hockey puck traveling at of mass m traveling at speed v, distance r away from the pivot, coming in at angle 90, so sine theta. Okay, it hits, and when it does, it's going to make this spin. It's going to give us angular momentum. But what if this object had twice the mass? It had the same velocity, hit the same distance, same angle, but had twice the mass. Well, this is going to spin faster. So there was more angular momentum in this case. What if it had the same mass as it did initially, but now it's going twice as fast? Well, again, if it's hitting twice as fast, it's going to make this spin faster. It had more angular momentum. What if I took it here and I had it hit uh, maybe at the halfway point? Well, if it hits at the halfway point, this isn't going to spin as fast, right? In fact, it's going to spin half as fast. And in fact, if I had it hit at the axis of rotation, this wouldn't spin at all. So therefore, the angular momentum of that ball with respect to this point would be zero, because if it passes through here, it's not going to cause any kind of torque. It's not going to make the system spin. Another thing is, what if it hits at an angle? What if instead of the ball hitting this way, what if it collided in this direction here? Well, in that case, it's going to have less tendency to cause this to spin. So this is also going to be a factor in determining what the angular momentum of that ball is with respect to the spinning board. So, and this is just trying to show you, like, if I'm trying to, actually work it through. So what I'd say is, okay, here's this ball is traveling at speed v. So I'd say m times v times r times the sine of this angle here, so sine of 90. Take the same thing. Now the ball is going this way, so it's still mass m, still traveling at velocity v. It is passing at distance r away from this pivot point, but now it's at this angle theta. So let's look at this here. I have objects shown below. Each have a mass of 2 kilograms. They each are traveling at 2 meters per second, and the black dot represents a pivot point, and the dashed line represents a line of action. Let's just see what the angular momentum of this ball is in each of these cases. So in case one, I have a ball of mass 2 traveling velocity 2 at a distance of 1 meter away from the axis of rotation, and it's coming in at a 90-degree angle with respect to the line of action. Therefore, I get 2 times 2 times 1 times 1, which gives me angular momentum of 4, and that'd be kilogram meters squares per second, but we won't worry about that right now. Now, by the way, this object is going this way, so if I curl my fingers that way, they're pointing away from the screen. That means it's a positive momentum. So in this case, I'm going to have it going the opposite direction, just to make that point, okay? So now it's still got a mass of 2, it's still traveling at 2, but now it's 2 r's away and traveling the opposite direction, but at a 90 degree to the line of action. So I'd say I have a mass of 2, my velocity is now negative 2, uh, and my r is 2. I'm still at sine 90, so that means it's negative 8 kilogram meters squares per second. Well, now I'm going to have it coming in at this angle here. So I have 2, a mass of 2 times a velocity of 2 times a radius of 1. In this case, it's a sine of 30, which is 1/2. And so I end up getting is 2 kilogram meters per second, 2 kilograms meters squared per second, okay? So you see, that's how all of these come into play in determining the angular momentum of an object traveling in a straight line. So again, I think this is a way that it helps me think about this. I know when I first had to process this idea, as a physics student, I thought, oh, here's a great way of thinking of it. Now, I don't know if they have these here in Korea. I think I've seen them. So in America, we have, at least when I was a kid, we had these things called merry-go-rounds. It basically was a big spinning disc that you could stand on, and your friends could push it, and you go around in a circle until you threw up. Okay. So basically, what I've got here is I've got a person with mass m standing at the edge of this rotating platform that has a mass of 6m and radius r. Right now, the person and the disk are both at rest. So that means the angular momentum of the system is 0. Okay, but now the person is going to jump this way, and when they do, the force with which they push themselves this way is going to apply a torque to this disk and make it spin. And so the angular momentum of this person has to equal the angular momentum of this. So the question then is what is the angular moment if the speed of this person is vp for person, what is the angular velocity of this in terms of vp and r? So what I would do is I would say, well, the person's going in a positive direction, whether it's using the right hand rule, and the disk is going in the negative one. So I'd say the angular momentum of the person plus the negative angular momentum of the disk added up to 0. Therefore, I can just move this across and say the angular momentum of the person is equal to the angular momentum of the disk. So I'm just going to take the person and say mvr sine theta. So the mass of the person times the velocity of the person times the radius r, and they jumped at a 90-degree angle. But for this, it's a solid disk, so that's 1/2 mr squared, and the m is 6, so it's 1/2 6 mr squared times omega of the disk. So let's see what we did here. Let's see. I divided this side by m. So both sides got divided by m. And I said 6 times 1/2 is 3. So I got VPR equals 3r squared. And I took this and I made it equal to a velocity of the disk over r. This look familiar? I'm going to divide both sides by r. And when I do that, what happens is actually what I did here was, what did I do here? I'm not sure what the next step was. Oh, I just divided this one. I did in 2 steps. I don't know why I did that, right? I divided by r, and then I divided by r again. Okay, whatever. Okay. All right. And what I get then is 1/3 the velocity of the person equals the velocity of the disk. So therefore, the omega of this is equal to Vp over 3r. Okay. In other words, it's a third. Let's try it in a different way. Now let's have a ball traveling towards a disk and getting caught in a basket. Well, it's going to cause, when it gets caught in that basket, it's going to collide and make it spin. Now this is this is a little bit different because this is a perfectly inelastic collision, right? So this, when it hits here, is now part of the rotating system. So it's just like 2 cars colliding and sticking together. So again, I want to find what the angular velocity of the disk is after the collision. So now I'm calling it a ball of mass m instead of a person. So I'd say it's just it's the rotational equivalent of a perfectly inelastic collision, where I say m1v1 plus m2v2 equals the sum of the masses times the final velocity. So what is the momentum here? Well, the momentum here is mvr sine 90, because it's coming in 90 degrees with respect to the line of action. This is at rest, so I'm just going to call that 0. Afterwards, what have I got? Well, I have right here, I have m r squared for that, plus this one here is a solid disk. That's 1/6 mr squared times omega final. And so I just solved this. So now I have this. Let's see, sine 90 is 1. I'm going to add these together. So 1/2 of 6 is 3. 3 plus 1 is 4. I'm going to divide by m, and I'm going to divide by r, and I end up getting that the final angular speed is v over 4r. But what if it came in at an angle? Instead of coming at 90 degrees, it comes in at 30 degrees. Well, we should end up with less angular velocity afterwards, right? Because it's only the component of this that's acting at a right angle to this line of action is going to cause a torque. So I'm going to start at the same place, but now it's going to be different. The only thing that's going to be different is, instead of mvr sine 90, it's mvr sine 30. All right, everything else is the same. But when I solve this, I end up, because this had half the angular momentum to start with, I end up with half the angular velocity afterwards. What if it came in at a 90 degree, at an angle of 0 degrees? Okay, if it came in this way and just went thump, notice it's not making any torque at all. So if I'd say mvr sine 0, that gives me 0. So that means the final rotational velocity is 0. Now, one thing about angular momentum is it definitely applies to orbiting systems. When I have satellites in orbit around an object, so we have gravitational things, there's no external torque acting on the system, so therefore the angular momentum of the system must be conserved. So let's just say right now I have the planet that's in this position here. So what I've got is I have m, v, r, sine 90. Okay, as it goes around and gets to here, I haven't put a torque on it. I haven't. There's been no outside torque acting on it, so it can't have gained or lost its angular momentum. So now what I find is m is still the same, but now I have 3 times the r. So that means that the velocity must be 1/3 of what it was. Otherwise, I would have gained or lost angular momentum. So it's really easy to solve it. If you're 3 times farther away, you have 1/3 the velocity. And we talked about that when we're studying gravitation, circular motion, but it was a little bit harder to understand in terms of conservation of energy. But it's very easy to understand in terms of conservation of angular momentum. I'm not sure why that one was blank. I'm sorry about that. All right, now let's try this one here. So I've got a diagram. Again, it's this top-down view of this board that has its COM is here. Now this board is just sitting on the ice. It's not anchored to the ice in any way. I have a hockey puck coming in. It's going to hit this board of 2m at this distance here away from its center of mass. So it's going to collide when it was here, and then afterwards this object is going to end up moving away and rotating as it does. It's going to go right. So the question is, in this case, is linear momentum conserved, and in this case, is angular momentum conserved? All right, well, here's what we find is, yes, linear momentum must be conserved because there was no outside force acting on it. Right, so the only force we had was an internal force between this object and this object. And so since the impulse in this direction equals the impulse in this direction, that tells us that linear momentum is conserved. So if I said the linear momentum of the hockey puck plus the linear momentum of the board, which was 0, afterwards, we could say whatever the momentum of the puck is plus the momentum of the board equals what it was to begin with. We must have conserved it because there was no outside force acting on it. Was there an outside torque acting on it? Well, the answer is no. There was no outside torque acting on it. So therefore, we must have also conserved angular momentum. So, it says P puck. I'm going to change it. It should say L puck plus L board equals L puck plus L board. I'll change that on the document. Sorry about that. I don't want to go back and redo this one. I knew I'd make a mistake. I always make a mistake. I'm not going to redo this one. But anyway, this is supposed to be L for angular momentum of the puck plus the angular momentum of the board equals the angular momentum of the puck plus the angular momentum of the board. All right. So let's just keep going here. All right. Now we're going to do it a little bit differently. Now, same system, except I'm going to have this end of the board anchored to the ice on a frictionless pivot, but still it is anchored, right? So I'm going to force it to pivot around this point right here. It still has a mass of 2 and a length of, in this case, the length of is L, okay? So the question is, in this case, when it hits it, is linear momentum going to be conserved and is angular momentum is going to be conserved? Well, let's just see what the case is. In the case of linear momentum, the answer is no. And let's look at why. And this is just a reasoning thing. So when this ball applies a force in this direction to the board is going to apply the same force this way, right? So if that was the only force acting on the system, then I would end up conserving momentum. But there is another force acting on it. This board wants to move this way, but it can't. The center mass of this board is not going to travel in this direction because it's anchored here. The center mass of the board is going to go around in a circle, right? Uh, but it has a net motion of 0. So therefore, I know that have not conserved linear momentum because there was an outside force acting on the board ball system. But what about angular momentum? Turns out for angular momentum, yes, it is conserved, and here is why. Again, I have a force of the ball on the board is equal to the force of the board on the ball. But Mr. Sampson, there's also this force here. That's true, except look where this force acts through. It acts through the point of rotation, and therefore it applies no outside torque, right? So if remember, torque is equal to force times radius, and the radius here is 0. It's passing through the axis of rotation. So this does not produce an outside torque. So therefore, the angular momentum of the system must be conserved. Let's go ahead and calculate that, and we'll be done for the year. You ready? Okay, so here I go. The puck is initially traveling at velocity v. It came to a stop in the collision, and it collided with a 2m board. So what is the angular velocity of the board after the collision? All right. Well, here's what we know. We know we're conserving angular momentum because there's no outside torque acting on the system. Remember, this force was passing through the axis of rotation, and since that made the R was 0, so force times 0 is 0 torque, so therefore it is conserved. So the angular momentum of the ball prior to the collision was mvl sine theta. So mv, this would be the length of the board times sine of 90. Plus, the board was at rest, so I'm not even going to bother writing down all of the symbols for it. It's just going to be 0. Afterwards, the ball came to a stop, so its angular momentum is 0. But the board was now rotating. Now, one thing you need to know in this case, and again, you'd always be told this, you don't have to memorize it, is that the moment of inertia or the rotational inertia, if you prefer, of a board that's rotating this way around its end is 1/3 ml squared. So instead of r squared, we just do L for the length of the board. Okay, so I'm going to take this here and I'm going to say, well, but it is a 2m board, so the angular momentum of the board afterwards is 1/3 2m L squared times omega. So now, since sine of 90 is 1, I get mvl is equal to 2/3 mvl squared omega. And now I decide here is I'm just going to divide this side by this side, which gives me this here. And I can get rid of my m's. I can get rid of one of my l's, but not one of them down here. And since I'm dividing by a fraction, I'm going to invert it. So I'm going to have 3 over 2. So I end up with omega is 3/2 VL. Okay, there you go. Thanks for watching. You are done with your AP Physics instruction for the year. All that's left is to take your test on momentum and then review for the AP test. Guys, I've really enjoyed it this year. Hopefully you have too. I'll see you in class.